Binary numbers. Okay, so we've all heard that like binary numbers are just a bunch of ones and zeros. This is how computers work, right? And I have a question. What? What? Does that mean this? Is this what's happening in my computer? Is this? Is this happening in my computer right now? So I started thinking about this, and I really wanted to get to the bottom of like why this works. And actually, this all came about because I was looking at thinking about Unicode, and I was like, how do all these things go into 8 bytes? All the like thousands and hundreds of thousands of different glyphs go into 8 bytes. So I just started doing a little research on like how this works, and it just led me to like go down this whole rabbit hole of figuring out how this stuff works. So this is kind of like a big overview of all this. So the first thing I want to talk to you guys about is the secret world of analog within the world of the digital. So this is sort of what the inside of a computer looks like. It's a bunch of wires and things made out of like materials that you can pick up and touch. There is actually no kind of magical world that looks like, you know, a green diver jumping into a green swimming pool. It's all analog. This is all just like electrons flowing through these circuits. And analog is all prone to noise. It's just a crazy, it's like the crazy natural world of physics and particles bumping into each other. So you have this noisy signal. But binary and digital is the idea that we can kind of draw this arbitrary line between what's high and low voltage and say below this line is a 0 and above this line is a 1. And that's where you get the idea of like ones and zeros in digital. And you can pretty much encode it into any medium. This is a player piano roll. Punch cards. This is actually a hotel key I just figured out. CD-ROMs, these QR codes, Redstone, these are all examples of just like ways that you can take just about anything and make it into an on or an off. And so I want to talk to you a little bit more about like how we do practical things with binary. So binary is really scary. So let me, like, if you're not really familiar with this, but you don't do a lot of low level, by the way, who here does do a lot of like low level bitwise stuff? Okay, cool, awesome. So you guys are gonna think that all of this is totally wrong. You have like a lot of notes for me after this, but but that's okay. So let's talk about just decimal numbers instead. Decimal, there's one rule that I want to talk to you guys about that I want you to remember going through this, which is when you run out of symbols, you start a new column with 1. So you get to 99, switch over to 100, and so on. So the number 10 is really totally arbitrary. You have 10 fingers on your hands. They look like this. And you notice that like at the end, you get this 1, 0 because you kind of ran out of different numbers to use. So we're just going to move one column over. So like if you had 12 fingers, it would look something like this. And these numbers actually have names. That's dec, L, and do at the end. And there's this great YouTube talk about this on Numberphile that talks about why the world would be better if we did use 12 instead of 10 for everything, because you can divide it more easily into different sizes, like 3 and 4 are divisible. But anyway, check this YouTube out if you want to learn more about that. It's pretty cool. So binary is the same idea, but just different number of digits. So just get 1 and 2. Just move that 1 over to the next column. So same rules, run out of symbols, start a new column, run out of symbols, start a new column. It's just that you only have 2 symbols. So we always talk about bits and bytes just to show you what those actually are. So a bit is just any one of these numbers, and a byte is what we normally talk about is 8 bits put together. And there's also a thing called a nibble, which people don't really use, but it's 4 bits. You're probably familiar with this too, that each of these goes in kind of a power of 2. So the value of each of these blocks, instead of being 1, 10, 100, 1,000, you have 1, 2, 4, 8, 16, using powers of 2 going up. And in 1 byte, you have, if you add all of these together, you have the range between 0 and 255. So that's where you've probably seen this number come up a lot doing web programming, doing pretty much anything. And that's why. So bytes are often represented as hexadecimal numbers. You get 2 hex digits for 1 byte. So it's a range between 0, 0, and FF. And what does that hand look like? It looks like this. So yeah. And we just do that because it's a lot easier to work with than these numbers. So let's try a little bit of binary number figuring. So anybody want to throw out what that first number is? 9,001. Okay, so this will maybe help a little bit. So you say, yeah, you're right, that's 9, you got 3, 13. And arithmetic basically works the same way. If you add these numbers together, you carry the 1 over. Works the same. Multiplication works the same way. And the next question really is, where do I put all this stuff? Like, how does this stuff work in my actual computer? And this is just sort of an abstract concept of like how memory works. Is just this huge machine. Tape roll. This is actually a picture of a Turing machine that I found online. So a Turing machine is this hypothetical concept. You may have heard of this too, but maybe you didn't ever think about it too hard. It's this long, infinitely long tape that you can write, and a machine that can write 1s and 0s onto that tape and also execute instructions based on what's written on the tape. So this is not, it's a very abstract and weird way of thinking about computers, but it also is sort of accurate in how memory really does work in your computer. This is a great quote that I'm going to skip over. So next question. How do we actually use this in JavaScript? So first, let's just step through some of the data types that we use day to day. Booleans are 1 bit of data. This is very simple. It's either true or false or 1 or 0. Numbers, bigger numbers, whole numbers and integers. Integers are just, we basically covered this. This is how integers work in binary. You would convert them the same way we just did all the math that we showed before. How many 1s and 0s, or the size of that integer. We don't really have this in JavaScript. This is more like lower level languages. All this still applies in JavaScript, I mean, in a way, because this is all, it's all kind of happening at some level in your computer. But you can have different sizes to your integers. They could be like 8, 16, 32, 64 bits. And you get bigger ranges of numbers depending on the size of the bit range that you allocate to that number. Signed numbers, ones that are negative or positive, are basically the same thing, but they're shifted over. So you get kind of half the maximum, but you have the possibility of making it a negative. So instead of 0 to 255, you have negative 127 to positive 127. Okay, so decimal numbers. This is where it gets a little more complicated. So you've all heard of floating point numbers. And they are used to basically expand the range of numbers. So you can get very large or very small numbers. But you also sacrifice some accuracy for that range. But they're able to basically use the same amount of memory as an int, but get just this vastly different range. So the way it works is really complicated, but I'm going to try to explain it anyway in a way that's probably still confusing. So you have 24 bits that determine the base number that all represent a fraction of a number. So you get something sort of like this. So let that sink in for just a second. So you add up all these different fractions together to get a base number. And then you use 1 bit for the sign, whether it's positive or negative. And then 7 bits for an exponent of 2. So you multiply 2 to the power, you get 2 to the power of whatever this number is, and multiply all that together, and that's how you get some arbitrary number like this. So the result of that is sometimes you have situations like this where you're trying to add 2 floats together, and it's not what you think it would be, because like I said, you sort of sacrifice some of the accuracy there, because you're really doing this really weird, complicated math equation behind the scenes every time you use one of these floats. It actually comes out to this, which sucks. How many people have been stumped by this before? Yeah. Okay. Well, lucky for the rest of you. So objects, to grossly oversimplify this, an object is really just a collection of smaller data types that are all kind of lumped together in one memory location or in one like set of references to other memory locations. It might look something like this in memory. So there is more metadata involved here, sort of describing how big each of these chunks of memory is, but this is and how they all go together into this one object. But this is the gist of it. There's also this concept of pointers. So even though we don't talk about pointers in JavaScript, we still use them. So anytime you're talking about an object, you're using a pointer behind the scenes somewhere. They're basically like this idea of you store the memory location of an object and how much memory you're expecting it to take up so that you can go there and find that. And that's how you can sometimes have two things that are representing the same object, like two different variables that are both editing or both assigned to the same object. Those are just really like pointing to another bit of data that's in memory somewhere. In JavaScript, arrays are basically objects also. They use an ordered set. This could be as simple as just like 3 numbers, the location in memory, their size, and the number of items that you have. Lower level languages will sometimes ask you to specify how many items are in the array, like whether you know or not. JavaScript is fortunate to be able to flex with the size of your array. You can have an arbitrary number and it knows how many items are in there based on how many you've assigned to it. And it's basically the same as in JavaScript. Arrays are really just sort of a syntactic sugar around an object that has these keys that are numbered. So this is sort of what's going on in the background there. To talk about text, first let's just break down how characters work, like the individual letters, numbers, and other glyphs in a string. This is pretty simple. It's kind of like those simple ciphers where you say like A is 1, B is 2, C is 3. It's that basic concept, but applied to all the characters. So ASCII is the most basic kind. Older computers use this. And there's 255 characters that you can do in 1 byte. And so 1 character in ASCII is 1 byte always. And there's just a lookup table for those. So A in ASCII is 65. Looks kind of like this. Unicode is way more complicated. There's over 1 million glyphs. It allows a huge number of characters to be represented in as few bits as possible. So it's actually like a sort of form of data compression. The way it works is really cool. One of the bytes, the first byte has some bits in there that indicate how many more bytes to expect for that 1 glyph. So if you're in that most common set of characters, you're only really using 1 byte. And you're getting the smallest possible allocation of memory for that 1 glyph. And further up in the higher numbers in Unicode, you're using up to 6 bytes here. And yeah, but what's cool is that you're like getting this message at the beginning telling you how far ahead to look, which is how they're able to kind of compress that data so small. Strings are essentially arrays of characters, taking each of these glyphs and putting it all together in 1 chunk. In C, for example, a null character, which is just a bunch of zeros, marks the end of your string, so you know when to stop looking ahead in your array, so you can determine the length of it. And something, behind the scenes, something similar happens with JavaScript. Digital music, just to talk about some other more abstract concepts, like digital music is essentially just taking the waveform of an analog audio signal and using 16-bit integer to sort of say it's approximately this loud at this point in time, and then doing thousands of those all stacked together, you can actually simulate a analog signal. But if you looked very closely at a really low bit rate or low sample rate, you can start to hear and see those that degradation of it into these like stair steps of sound. So images too. Well, like let's talk about hex colors for a second. You guys want to test your might with this? Everybody know this? Everybody. Red. Green. Wait, okay. No. Huh? No, okay, it's purple. So yeah, these are all just saying like this is a little bit reddish. There's a little bit green, sort of blue. These are each representing like 1 byte representing each channel. So colors like that are 24 bits in most situations. Also 3 bytes or 6 hex digits. Sometimes there's an alpha channel too, which makes it 32 bits. And each of those color channels has 256 possibilities for their magnitude. And so when you look at an image, it's really just like an array of colors. And there's some other metadata saying like how wide or tall it would be. And you can actually look into any spec. Like if you want to look at the PNG spec, it's kind of interesting because it tells you the recipe for writing a PNG in binary. And there's all the metadata for like what type of colors it's using and whether it's 32 or like has transparency or not, that kind of thing. But yeah, so it sort of looks something like this, just ones and zeros on a bigger scale. Everything else is somehow related to this. Find something that's not ultimately ones and zeros, or maybe you can now start looking at everything as if it is ones and zeros and think about how it might be built. And I hope that this phrase now means something better to you, more useful to you. So that's that. Thank you. Yes?
How many bytes does a character in JavaScript is consuming?
So JavaScript is generally using UTF-8, so it varies in size, like the way that you would actually compress it. And also, you may have noticed that this is not very JavaScript specific, so I actually don't really totally know.
The answer is 16.
16? Okay, UTF-16.
The reason I know this is that because I used to play with PDFs, generic PDFs in JavaScript.
Yes.
And as a result, Unicode is not fully represented in JavaScript.
Okay.
Because there's a lot of problems. So just a lesson to everyone, keep your strings in UTF-8.
All right. So I have some more JavaScript stuff, specific stuff here, or I can answer some questions too. But if you guys have any, no, we good?
We're good on time.
Okay, cool. I'm going to go on and do some bonus questions. Just talk about how we do some of this stuff, like manipulating actual binary stuff in JavaScript. So there's a bunch of kind of newer APIs out there, typed arrays, array buffer, data view. These are all things that are for working with streams of data. So like if you take a file from your hard drive, you can convert that just straight into ones and zeros and work with it chunks at a time, doing whatever you need to do with it. And I also wanted to talk to you guys some about bitwise operators. So these are these other things. The thing that whenever you try to do an and you forget to do 2 ands, and your code doesn't run right, I'll explain why. So first of all, if you want to actually deal with and see how these things are represented in binary in JavaScript, if you want to convert a number to a binary string, there's no way to write like a literal that's like 1001111 and have that do anything. It's going to be the decimal version. However, you can work with strings that are binary. So using toString, you can give it a radix, which is the number that it's going to use as like the base for that number. So number toString 2 will give you a binary string. And the inverse of that is parseInt with the number 2 as the radix. So these are all these sort of logic operators that work on a binary level. And the way that they work for all of these is to take the number on the left and compare each individual binary digit in there to the number on the right. And what we're looking at right now is not actually JavaScript code because this is in binary. But if you had, for example, like, it still works with decimal numbers. So if you had like 3 and 7, that would still work the same way. But I'm just showing you in binary, so it makes sense. So and finds everything that is, if it looks at every single number, 0 or 1, and decides if in both numbers it's a 1. If both numbers it's a 1, it outputs a 1. If not both numbers is a 1, it outputs a 0. And the bitwise OR works kind of like an OR would. So it takes anything that's a 1. If either one is a 1, it outputs a 1. And the XOR, which is the exclusive OR, is like an OR, except if both things are 1, it outputs 0. So they have to both be different for it to output a 1. So in this case, like you have 1 here and 1 here, so that equates to 0. A few more. This is the not. It basically gives you the exact opposite in bits. So 1, 0, 1, 1 becomes 0, 1, 0, 0. The shift left is literally adding zeros to your number and moving it all. So like shift, and you're telling it the number on the right is actually the number that you're shifting it over, the number of zeros you're adding. So it's equivalent to multiplying it by 2 for every one of these. I think I said that right. Likewise, the shift right is adding zeros on the left side and dropping off the stuff on the right. And I'll show you how you actually would use this. This is kind of like not very helpful until you start using it for something practical. So this is a really common little bit of code. And it's basically getting the components of a color that's written in hex format. So first of all, I'm writing down the, I'm defining the offsets for all the different channels. So blue is at 0, because that's the first set of, if you're looking from right to left, blue would be the first 2 digits, right? The next one over would be green, and that would be 8 bits over 1 byte over, because we have 1 byte per channel. And then red is 2 bytes over, or 16 bits. And then a channel mask is, I'm basically saying that the possibilities are between 0 and 256, so FF in that case. For each of these, I'm sorry if this is not making sense. I realize this, I just starting to realize how obscure this must look. But so if you give it a color, you're basically saying I'm going to shift that color over so that I am just getting the red. The triple right arrow, or right bracket, is going to move it over that many spaces in bits. So in this case, it's dropping off the first 16 bits, and then doing a mask to get just the first eight bits of that number. Let me actually show you this. I have this slide as the same thing that we just were looking at, except in binary. It actually makes a lot more sense. So this is our number, orange, FF6633. So this is how it would look in binary. The channel mask looks like this. It's a bunch of zeros with 1, 1, 1, 1, 1 at the end. So for red, first thing I'm doing is I'm shifting it over 16 bits. So I'm basically dropping off all of these 16 bits. And you end up with just the red channel here. And then I'm doing the intersection of this number, 1, 1, 1, 1, 1, 1, 1, with this one. And since they are all ones, every place where there's a 1 in both numbers, it's going to output a 1. So we end up with the FFF, or the FF for the red. For green, this time I'm shifting it over 8 bits, which is just dropping off the first 8 numbers, 8 bits. So I have this number left. I'm intersecting that with this. So this Remember, this actually is this number, like 0, 0, 0, 0, 0, and then 1, 1, 1. So because only that this last portion of it has ones in it, only this thing is going to stay. So you drop off all of these numbers over here, and that's how you end up with the green channel. And then the blue is the same thing. It doesn't shift over at all, but we do the mask here, and we only are seeing this output. So all this goes away. So does that make sense? Anybody have any questions about that? There are other cool things you can do with this too. Like you can take, for example, if you have a bunch of different flags or like Boolean values that you want to store all in one. So like say, an example I've actually used is on a video game where you have like a tile where maybe your character can only cross through like the left side of the wall or the top of the wall, but not the bottom, like they'd bump into the bottom or the other side. You can store each of those as Boolean values in a binary number and like find the specific value based on a mask like this. So, yeah. Anyway, any other questions?
Any questions? All right, give it up for Mims.
All right, thank you.